This is time for you to ask questions for a few minutes until like 5:10 a.m. apparently. Okay, you could go first.
To find the orthogonal.
The orthogonal.
Yeah, orthogonal, right? Do you have to use which rule do you have to use? Scalar multiplication. Okay.
So when you're finding orthogonal vector, let me go back to my lecture from week 1. So here in the notation, you see on the bottom, it says if U dot product V equals 0, then they're orthogonal. So that means dot product. I explained before in the lectures what dot product means. So if we have, just going to go over very quickly. So if we have, let me use this. We have U equals to 1, 2, 3, and V equal to 1, 0, 1, for example. This here, this is one vector. This is U. This is another vector, V. So when we're doing U dot product V, it means this one times this one, so 1 times 1 plus this one times this one, so plus 2 times 0 plus 3 times 1, which obviously here will give you 4. Okay? So in this case, these vectors are not orthogonal. And if you want to look at it in the point of geometry, yes?
What do you mean that they're not orthogonal?
What does that mean? Well, the orthogonal is basically saying that you have two vectors are perpendicular. People are familiar with the word perpendicular? That's what orthogonal means. It has the same sense. If we look at in a geometric point of view, we have this. And say I have a vector going this way. That's one vector. Let me call that U. Here's another vector. Would you say these are perpendicular?
Yeah.
Yes, okay. And people usually realize it because it's a 90-degree angle or such, right? What the dot product tells you is a projection of this vector onto this one. If we did the reverse, it would be the projection of this onto that. So right now, if we have, say, other vectors like this, right? This is not orthogonal if we're in the xy plane, right? Because it has a projection. This is the magnitude of the projection right there. But if they're in 90 degree, it's 0. There's no distance. There's no projection. That's what orthogonal is saying. If you want to think it as being a right angle, or let's not say right angle, perpendicular, it's the same thing. Okay? So, but basic formula is U times V, and if it gives you 0, U dot product V. If it gives you 0, that means they're orthogonal. Okay? There's infinitely many solutions to question 3. Remember we had gone with the transformation of variables? We had xy equals something. We had one equation, right? We said, what if we let x equal t, for example? So now we have t plus y equals something. So y is going to equal something minus t. That's the form I want you to write it. I want you to change the variables. It's basically what it's saying. It's almost redundant. It is redundant, but this is a systematic way of approaching the problem, just so you get a further understanding. So there is a solution, but it's not like a particular value. You'll be in terms of t. That's why I say use arbitrary variables.
3 variables and 2 arbitrary variables.
Exactly, but the third one could be written as, if there's 3 variables, the last variable, the third variable, could be written as 2 arbitrary variables. So let me go over that real quick. So I think I have x2 plus x1 plus x3 equals to 10, right? So we have x2 plus x1 plus x3 equals 10. I said use variables t and s. So let me say x1 equals to t, and x2 equals to s. So x3 is now equal to 10 minus t minus s. That's your solution. So x1 equals t is your solution, x2 equals s is your solution, and your solution for 3 is x3 equals 10 minus t minus s. Yes? So for him first and then.
So for that question, you want us to find like every possible way to do it like that?
Well, I just want you with t, and I might use an example. So right now we have infinite many solutions. So you could say, okay, now let's say t equals to 1, and say x2 is also s equals to 1. Then you just plug 1 in here and you get 8. So that would be your solution to that equation. So that's how I want you to approach the next problems.
I was going to say that in other words, you're trying to substitute x1 and x2 and then isolate x3. So
Yeah. Yeah, we're saying we know that this is equal. We set this and we know this. We know x2 equals s. Even though they're variables, we know it. We set it. So now what is x3? Here is the equation we have, and we solve it by using t and s. It's very general right now. But this is the way to approach it. Okay. So I think everyone knows what a row picture is, but maybe not by definition. But if we think we have two equations, let's say minus x plus y, x equals 1, y equals 2. So here would be 1, right? And then we have x plus y equals 3. Okay. Just pretend we didn't know this. I'm just putting it there for simplicity. So we have x plus y equals 1, and x minus x plus y equals 1, and x plus y equals 3. So we want to solve this equation using a row picture. You could think of it as your normal x-axis and your y. And you know, most people are familiar with y equals 1 plus x. That's this change to this notation.
Well, x equals 1 and x equals 2 is supposed to be the second x, supposed to be 1.
Where?
On the side.
You made the
Oh, yeah, sorry. This is a y. That's a y, okay? So this is going to look something like, okay, when x equals 0, it's 1, and it's going to look like a line like that. Is that correct? And this one here, we could translate into y equals 3 minus x. So it's going to look like a slope like this. So this is your row picture, because we're taking the picture of the rows. These are rows. And so the intersection will give you this point, 1, 2. That's the solution to your problem. And there's only one solution. That's the intersection. Okay? So that's concerning the row picture. Now concerning the column pictures, we look at it a different matter. We say, okay, x times some vector. Here it's minus 1. We take the coefficients. That's a 1, that's a 1. Minus 1, 1. Plus y times another vector. And here, in this case, it's 1, 1. Gives us the solution of 1, 3. Okay? So this I'm calling column 1. This I'm calling column 2. The reason...
Where you got 3 from?
Because here. So this is a solution. This is what the equations give. And we basically want to find how many of C1s and how many of Y's give you this like last coordinate. So we look at it in a vector way, not what you're used to in the XY plane. So we look at it in vectors. So if I draw here, my vector for this vector C1 is minus 1 and then up 1, right? So it looks like this. And my vector for y, it equals 1 and 1, right? So we have to say this is 1, 1, and this is minus 1, 1. And we know our solution is 1, like 3 over here, for example.